All right, this time we talk a little bit about what things generate potential, and then we relate potential and potential energy to each other. I know that potential can be a hard thing to get your mind around at first because it's not entirely obvious why it's useful, although it does turn out to be useful, and it's a good way to conceptualize things. It will end up being tremendously useful when we get to circuits, where it has a physical analog that is pretty intuitive. It's like the pressure in a hydrodynamic system. So imagine you have stuff flowing in a pipe, then you have the motion of particles, and that would be what we call current, and then you have differences in pressure that cause that flow. And potential is essentially like that for electric charges. Right now, the charges aren't constrained by anything, so it's kind of like having just water spewing out, and it doesn't seem to make a lot of sense. When we get to circuits, when things are confined to wires, then that will be a more easily visual model to use. But for now, it's useful to sort of do in terms of the fields and energies of free particles. The basic rule is that the potential difference is created by the separation of charge. That if we take two charges and we pull them apart, then we create a potential difference between them. How do we pull them apart? Some sort of mechanical or chemical system, right? It can be simple friction, transferring charge from one body to another. As an extreme but interesting example, ice particles in clouds will often rub together, transferring net charge, so that the top of the cloud ends up being positive and the bottom ends up being negative, and they can build up to maybe 1,000,000 volts of potential difference between them. And then when that voltage difference the difference there between there and the ground gets too large, at some point the air will break down and charge will flow. You get lightning strikes. You can have separation of charge because of chemical reactions. This is how a battery works for the most part. A battery is a chemical reaction that separates charge until eventually there's a static voltage difference between two ends of the battery. Or it can be biological, which at root is really chemical anyway. Cell members, for instance, have potassium inside and sodium outside. Across the potential difference of about 70 millivolts. And there is what's called a potassium pump, that a reaction rate that keeps this going, even though the concentration would have it drive the other way. And that chemical reaction also creates this potential difference. Falling back on our easiest to understand example, we'll look at parallel plate capacitors. If there's two plates hanging out in space and there's no net charge on either of them, then a charge in between them feels no tendency to move one way or the other. In other words, if both plates of the capacitor are uncharged, then there is no electric field. There is no reason that a positive charge would be drawn to one side or repelled from that side or whatever. And so it doesn't. It takes no work to move the charge from A to B or anywhere in that space. But if we were to move some amount of charge, say some number of electrons from here over to here somehow, we physically carry them or we hook them up to a battery that pushes them out or whatever, and we create a situation where there's negative charge on one side and positive charge on the other, then it is difficult to move the particle from A to B, a positive one, because it doesn't want to get closer to the positives, it wants to get closer to the negatives, and so we have to do work on it. We have to do work on it to move it over, which will then create potential energy, which means there'll be a potential difference between this point and this point. Potential differences are measured by a device called, logically enough, a voltmeter. Not a voltometer, a voltmeter. Don't know why. Because we can set the 0 for potential energy anywhere we want, we can set the 0 for voltage anywhere we want, although only the once. But because of that, we can only measure differences. Right? We can't measure the actual potential at a location, only its difference versus some reference point that we pick. So every voltmeter has to have two inputs. Traditionally, the higher one and the lower one. The higher one is black, the lower one is red. That isn't important, it's just traditional. A voltmeter, therefore, always has two probes. All right, so we can pick the 2 points. Here we're picking across the two ends of the battery. The way a 9 volt is laid out, these are the two ends. Instead of being physically at two different ends, they're on the same face. A 9 volt battery, as measured here, seems to have a little bit more than 9 volts in it, which is not unusual, and we'll get back to why that would be the case, why we'd expect a little bit more than the rated 9 volts. Remember, there is a distinction between potential and potential energy. It's not great. We didn't pick the world's best terminology here, but we're sort of stuck with it. The two are related by the fact that the potential energy, U electric, is just the charge times the voltage. All right, the potential energy of some particle whose own charge is Q inside a potential set up by some other external charges. And generally, we don't let these move. We're saying these are the given structure, and this is what we want to talk about, what moves in it. The energy requires this charge. U electric requires something here, and therefore requires our particle as well. But the potential exists only because of the external charges. It doesn't matter whether there's a charge there to feel it or not. Going back to the other one, when we had a plate like this and like this, and we said that there were potentials, there's a potential gradient between them. That potential gradient exists regardless of whether we have any charges in this field between them. All right, the potential is defined entirely by the charges on the plates, and whether or not there's a particle inside this region to feel it has no bearing on whether the potential exists. The electric force is conservative, and therefore energy conservation still applies, which means, one, there might be a handful of problems of the sort you're used to where you have some kinetic energy plus some potential energy stays constant. So they might say, like, how far up a potential gradient will a positive charge go before it stops and turns around. We can do some examples here. Here's a convention we're going to use a lot coming here. They have drawn these dashed lines are places that all have the same potential. All right, so this is 500 volts. By definition, we'll just say that. And then I guess probably 80, 60, 40, 20, 20. Yeah, so 20 volt slices. So this is 480 volts, 460, 440, 420, 400, and anywhere on this line is considered to be the same voltage. All right. If we take a positive charge and it goes from a 500 volt line to a 400 volt line, it has given up energy because U electric is a smaller number here, Q times a small number. It doesn't really matter what the positive charge is, we just know it has definitely given up energy as it's gone from here. If it's given up potential energy, then it must have gained kinetic energy, so it speeds up. It gets faster. Right? It's lost potential energy, and so it's gained kinetic. We would generally say it's gone down a potential gradient here, which with the idea of something which is rolling downhill or so on, and the basic same idea. On the other hand, if we had fired the particle the other way, going from 400 to 500, then it is gaining electrical energy, gaining electric potential energy as it climbs, because it's Q times 400 here, and then becomes Q times 500, which is a bigger number, because delta V is plus 100. And so it has gained electric potential energy that had to come from somewhere. In this case, it would come from the kinetic energy, so the object has to get slower. Right? It must be slower as it moves over to this point. If the kinetic energy had been small enough, it might not even have made that point. It might have only gotten to like here and then turned around. All right, positively charged particle moves past the 400 volt line, moving leftward. It eventually slows down, stops, and reverses direction. When it passes the 400 volt line again, which of these must be true? That it's moving faster than it was when it was there the first time, it's moving the same speed as it was, or it's moving slower, or that you'd need more information. Of course, here we have, since the energy is conserved, that whatever it has put into the potential energy by moving this way, it gains all of that back as kinetic energy here, and so it moves at the same speed. This is exactly analogous to just throwing something upward in the gravitational field, where it loses kinetic energy until it comes to rest, and then it gains back every bit of kinetic energy as it had on the way back down. All right. For many applications of charged particles, the energy that a joule represents is just much too large to be convenient. For nuclear and subatomic particles, it's inappropriate. It's humongous. A joule for like an electron is a staggering amount of energy. Thus, we define a new energy unit, the so-called electron volt, symbolized by EV, lowercase e, capital V. And we define this as the kinetic energy gained by an electron in climbing through 1 volt of potential difference. As a quick aside, how come the electron gains energy as it climbs the potential difference? Because the potential energy, remember, is minus the potential. So a positive voltage difference gives us a decrease in energy, potential energy, which means it is an increase in kinetic energy. That's that weird back and forth that we've all been cursed to by Ben Franklin's unfortunate choice. Why do we define it in terms of the electron? Because the electrons are the things that move more easily. And as we've said before, committees are a little bit obsessed about you remembering that it's electrons that move around. It's pretty easy to convert an EV to SI units because we really just have, it is literally just an electron times 1 volt, charge on electron times 1 volt. Charge on electron is 1.6 times 10 to the minus 19 coulombs. So we get this, and a coulomb times a volt is a joule. So we find out that 1 electron volt is 1.6 times 10 to the minus 19 joules. Pretty easy to remember because it's the same numerical factor as the actual charge itself. That is, of course, no accident at all. Although the joule is too large a unit of energy for atomic problems, it turns out the electron volt is usually too small a unit of energy. Oops. So you'll usually see energies in the keV, MeV, or even GeV range, the kilo electron volt, mega electron volt, or even giga electron volt range. Even higher sometimes, although these tend to be what we are able to produce in our particle accelerators now. Linguistic warning, just to keep this in mind, the electron volt is not a voltage. It's not a measure of voltage. It's not voltage in any way. It's a unit of energy, because it's a voltage times a charge, which is always energy. This is similar to what happens with the light year, which is not a time, but a distance. Even though it has the word year in it, when we take a light year, it's the speed of light times a time, so it gives a distance. Just keep that in mind. It's again sort of a weird and not particularly great choice we've made. It becomes second nature. I won't ever argue that it's smart, but eventually you get used to it. All right. Protons released from rest at point Q, where the potential is 0 volts. Afterwards, what can we say about this proton? Does it remain at rest at Q? Does it move towards P at a steady speed? Does it move towards P at an increasing speed? Does it move towards R at a steady speed? Does it move towards R with an increasing speed? We, of course, know that positive charges flow down potential gradients because they want to have lower potential energies. So it will move towards P. It's a little trickier to say, well, will it get faster or not at a steady rate? And it will increase because there's a force on it there's a force between these 2 points, which means there's an acceleration, so it will increase have increasing speed.